billion of years to solve that problem. So it's interesting though that if you made a so-called quantum computer, this is a computer that doesn't exist today, but doesn't exist today. But there are hopes that it will exist in the near future. But these new kind of quantum computers that people are working on, they operate in a way which is fundamentally different from any regular computer that we have today, and could solve very efficiently this problem of factoring. And you might ask, why do I care about this problem of factoring in the first place? Who cares if a quantum computer can solve that efficiently? And the reason is that the way information is transferred securely over the internet currently relies on the fact that factoring problem for large numbers is extremely difficult, right? Even for very sophisticated computers to solve. And if you could make a quantum computer, suddenly the secureness of information over the internet becomes highly suspect, right? Because now you can basically find the keys very efficiently. So that's why governments and lots of researchers are interested in part in building quantum computers, is to solve problems like that. Okay, so second problem. I guess everyone has seen geometric series before. Is that true? Or
yeah,
we did a little bit. Mostly we focused on arithmetic series, but I think I introduced the concept.
Yeah.
Okay, so how about part A?
Part A?
No.
What is the range of x if s is
We can solve B though.
What's
No,
s?
So S is that sum?
Yeah.
Oh,
Sum.
that doesn't say it. It's fine. Okay, got it. Correct.
Does anyone know what A?
What
No,
value?
but I know what B is.
Oh, okay.
To simplify it, guys, can you think of a value of x for which this, no matter how big n got, it would not go to infinity. It would stay small.
Zero.
What else?
One.
Anything else?
Well, let's talk about 1 real quick, actually. So that's interesting. So, yeah, if x was 1, then actually, maybe it's useful to replace that infinity up top with just a capital N.
Oh.
So when x is 1, what does that sum give us?
One.
No, it's a sum. Remember each.
Oh, so.
Why don't you do a few examples in your head? What does the first term equal, guys?
So are we like?
What's the first term? 1. What's the next term? 1. What's the next term?
1.
1.
Next one, it
So
just
therefore,
keeps going.
so then what does that add up? If you add up 1 n times, how many what do you get?
N times 1.
Infinite times 1, yeah.
Which equals?
N.
Sounds good. Okay, so if we're taking n to infinity, then that's going to become infinite, right?
Yeah.
Okay, so x equals 1 is sort of the border line on when this sum will actually give you a final number. So if you had, let's say, x equals a half, so that's, the first term is 1, the second term is a half, the third term is a quarter, and so on. So that becomes, every term in the series gets progressively smaller. And so you at least have a chance that it's going to be finite. So anyone want to now speculate a range of,
Oh,
for 8?
for 3 or?
For 2a?
Oh. Remember?
So think, guys. He just said.
X is less than infinity?
No, it's not.
1 and 0.
We already talked about that. If it's 1, it goes to infinity, so it has to be less than 1, right?
Yeah, basically.
Oh,
So what does it have to be greater than?
No, it can't. But it also
Zero.
can't be
Zero.
negative. Wait, no.
Greater than, less than equal to 1.
Wait,
We
no.
already said 1 isn't going to work.
yes.
And neither
less
can
than
negative,
1.
but negative 1 can't work either because then it would go on to negative.
Right, so then what do we have?
You have
0 on the.
So how do we define a range between
it would be
negative 1 and
1.
right?
It would be more than
I never taught them two-sided
More than
inequality, so they don't really know how to express
Yeah,
it.
that's a problem. But yeah, it's between -1 and 1.
yeah.
Okay, yeah, just got that. Just wrote
Okay,
it
so
down.
perfect. How about B?
Okay.
Oh, okay.
Evaluate.
I think this is actually a very cool problem. I think
that
it's
5 or
a
S?
neat trick to.
Is that a five?
That's
This is
yes. I don't think I've written any 5s on the right hand of
Okay.
the board. So it's all S's.
We wrote 1. There. 1, 2, 3, 4.
Do you guys know the trick for solving this kind of sums?
Evaluate
It's
S
a very
for
neat trick.
X in this range.
I can show you, or if somebody knows the trick, maybe you can go.
They don't know the trick for geometric, they only know
Okay,
for,
so this is I think ultra cool, so let me take a few minutes and show you.
Yay, Jason, you're still our teacher. We always have to be taught advanced math by Jason.
This is one of these things that's kind of very difficult technique to invent, but once you see it, it'll hopefully stick because it's so neat. So first I'm just going to write out, eventually I want this capital N to go to infinity, but for now I'm going to keep it as a capital N. And so this sum S, if I just write out all the terms, the little n equals 0 is just a 1, and then I get plus x, that's the n equals 1 piece, plus x squared, and so on, until I get to x to the n minus 1, and finally x to the capital N. Okay, so we agree that that's what S is? Okay, so now I'm going to look at, just multiply S by x. Okay, so x times S. Now I'll just multiply every term here by x. So this one becomes an x.
Plus
This
x
x
squared
becomes an
plus
x squared.
x cubed plus
And so on. This x to the n, that would become x to the minus 1 again. This x to the n minus 1 becomes an x to the n. Right? And finally I'm left with one more term, which is x to the n plus 1, which is what I get by multiplying that guy by x. So now if you stare at this, it's pretty remarkable because for just about every term that's in S, there's the same term that's in x times S, right? Because you can just see they match up, right? Except for the two terms at the end. So if I take the difference of these two things, almost everything's going to cancel out. You agree?
Yeah.
Okay, so let's just take the difference. So if I look at S minus x times S, so first of all I can just factor out an S. So that's S times 1 minus x. And so I get, I'm left with a 1. Right?
and n plus 1.
Minus this guy, minus x to the capital N plus 1. And now I can just solve for S. Right? So that means that S is equal to 1 minus x to the n plus 1 over 1 minus x. And now we can just take this n and replace it by infinity, capital N. And if we're dealing with, well, I erased part A, but if we're dealing with the range of x for which S gives us a finite answer, then what does this piece give?
finite answer, for a finite answer.
Oh, it was like the double.
So,
The answer was like two negative 1 ones.
so it would be 1 minus what? It would be plus 1.
Yeah, let's just look at the x to the n plus 1 for now. So for instance, you might even, so we agreed that, let's say for x equals a half, this sum should give us a finite answer. So if x is a half, we have 1/2 to the infinite power. What is that?
1/2 infinite power? Infinite. No. Half of infinite, yeah.
Okay, so I have to be careful.
Oh,
So I mean,
because,
1 over 2 to the,
because, yeah.
so this is equal to 1 over 2 to the infinity?
Yeah.
And what's 2 to the infinity?
Infinity.
Infinity? So this is 1 over infinity, which is?
Infinity, yeah.
No, it's 1 over infinity.
1 over infinity? Yeah. Infinity is the negative first.
No. Well, that's right, but
That's
what,
true.
if that's true, but if I have something, an object, and I sliced up an infinite number of times, how small are those things? It's gonna get closer.
0.
0.
0, exactly. Okay, so this x to
yeah.
the n plus 1 for n going to infinity, and for x between minus 1 and 1, that's 0. So I get a nice, beautiful answer, 1 over 1 minus x. So I think this is a beautiful trick that hopefully you guys will take with you.
Yeah.
This is how you solve geometric series. These things actually come up all the time in physics, so it's very useful things to have under your belt. Any questions on this?
Let's see.
Okay, so let's maybe get to 3.
Yeah.
Yeah, please.
So you should, I think you should pick 3, because if you choose, so there's a 1/3 chance of picking each door, and so you pick the first 2/3 of a chance for the other doors to have the $1 million in it, and so if so if door 2 has a shoe, then the 2/3 goes over to the door 3.
What a beautiful answer.
Good
That
job,
was,
Carly.
Just
Amazing.
perfect. Just perfect, actually.
So is that the right answer?
That's indeed just perfect logic, actually. Amazing.
Nice job.
So, everyone agree with that, actually?
Yeah.
So I think, actually, if you're a little bit,
But I still want the goats.
if you want the goat, the equation changes there. Although I think, given that the shoe was revealed, if you want the goat, you should still, for the same reason, right, you should still switch. Now, if you want to make this even more intuitive, you can consider a version of this problem where you have not 3 doors, but let's say you have 1,000 doors. Okay, you choose one door which you think might have $1 million, and then let's say of the remaining 999 doors, somebody reveals 998 of them, and shows you that there's not $1 million behind there. So certainly you'd want to change doors at that point, right? Because the odds that you chose initially the right door is extremely small. Right? Does this make sense? I don't know if I said that very well.
Yeah.
So yeah, I think if you think about it from that point of view, it's more intuitive. So actually, there's an interesting anecdote about this problem. There is a woman who I think was considered had the highest IQ or something.
Marilyn Vos Savant.
What's that?
Marilyn Vos Savant or Vos Savant?
I don't know the name of the
Yeah,
person.
she writes a Parade magazine.
Okay, yeah, you know the story. Yeah, so it's a very nice story. So she posted this problem, published this problem in this magazine, and there's a backlash from mathematical community. So even math professors and so on were writing angry letters saying this is preposterous, you're completely wrong. There's no way this violates all sorts of probability theorems and so on. But of course she was right for exactly the logic that was so eloquently by this gentleman here.
Macaulay logic.
So moral here is, even if people that are very well established tell you that you're wrong, it's not necessarily true. Well, so that was amazing. I am really in awe of what you guys are capable of doing once again. So before I leave you all, so maybe I'll just say a little bit more about how I got into what I do now. So I grew up actually on the East Coast of the U.S. And, I grew up in New York. That's where I spent my elementary school years, and then I moved to South Florida. And I went to college at University of Florida, the Gators. You've heard of them, if you're a sports fan. And I actually had no idea that I would be doing physics at the time. In fact, I started out as an engineering major, and eventually realized that I wasn't really so inclined towards more applied things, but I wanted to think about problems that were more fundamental. And so that's why I eventually switched into doing physics. And I have to say that was not an easy choice for me to do, because I knew that if I was going to make the switch to physics, I was going to get a PhD because I wanted to do something in research. And that was a decision which I did not take lightly, because as an engineer, you have the mindset that, well, after a few years you're going to go off, you just get your bachelor's degree, you go and get a nice job somewhere, and that's it. But graduate school meant 5 more years of school that I wasn't actually intending on. But I'm very, very glad that I made that decision. Graduate school isn't for everybody, but for what I wanted to do, it really was a delightful time. It's quite different from school that we do before that, even college, because you're much more free. You don't take a lot of classes. Really, most of the time in grad school, it's just doing your own thing, just pursuing ideas that you find interesting. And in most technical areas, actually, grad school is something you get paid for. So it's different from, let's say, if you go to medical school or law school. Generally, you have to pay a lot of money to get through those. And if you go to get a PhD in physics, you actually get paid to do this. You won't make tons of money, but you likely won't end up in debt after you get your degree. And so here I am. This is. I guess I should say I went to grad school in Santa Barbara, UC Santa Barbara, which is an awesome place to live. 5 years, both for physics and personal reasons. It's a beautiful, beautiful place. And I've been in Pasadena actually ever since. So I was a postdoc here at Caltech after getting my PhD. And then I went to UC Irvine for 2 years as an assistant professor there, and then moved back here after that. So it was this a path that I never expected to take, but I'm really glad that I ended up where I am. Get to interact with people like you, which is certainly a great experience. Yeah.
So what's it like working at a place like Caltech where it's filled with some of the world's smartest people?
It's awesome. Actually, I was a little bit scared to come here, to be honest. In fact, one of my friends put it perfectly. He said, I told him that I had a little bit of anxiousness about coming to Caltech, and he said, why? Because the undergraduates will be smarter than you. I said, yeah. Well, what I realize now after teaching here for 3 years is that even though many of the undergraduates are smarter than me, I have more experience, so I can still play a useful part in their development. So that's still a lot of fun. So there's still but I think surrounding yourself with as motivated and talented people as you can, no matter what you do, is a good thing, right? And one should never be discouraged from doing that just because you think you might not be able to match up. So you should really always take the best opportunities that are available to you, no matter what. This is something that I only realized within the last 5 years of my life. It's worth keeping in mind. Any other questions? Yeah.
How would you use physics in a quantum computer?
So the way, what a quantum computer, well, let's start by just thinking about how information is stored in a ordinary computer that we use today. So it's stored in terms of bits. You all know what bits are? It's like a way to digitally encode information, 0 or 1. Now, in any presently available computer, your bits are either zeros and ones, and that's it. Right? So it's a yes or no kind of thing. But in quantum mechanics, it's not so anymore. So in a quantum computer, your bits can simultaneously be a 0 and a 1 at the same time. And so that's a kind of degree of freedom that you simply don't have in presently available computers. And if you take advantage of those weird quantum mechanical properties, there are certain things like factoring enormous numbers that can be done very efficiently that kind of get shortcutted through these bizarre quantum properties. So that's in a nutshell what quantum computers do. They take advantage of certain properties that ordinary bits could never provide. Exactly, qubits. What we call them, quantum bits.
Okay. Question for you. Can you tell us a little bit what is a day in the life of a physicist like?
It's a wonderful question. So a day in my life, it varies actually wildly depending on the time of year. So I would say that typically I spend hours a day just talking to my collaborators. So this is something that you should definitely, well, maybe a stereotype which you should abandon is the idea of a scientist just working in isolation, antisocial kind of environment. That's most certainly not true. My day-to-day life involves talking to many people all the time. You make actually lots of good friends also through people that you work with. I spend a fair amount of time actually writing. It's another thing that's maybe useful to keep in mind. Nowadays, I really like writing. I never liked writing when I was younger, but I find that if I look at writing as a creative process, that I try to say things in interesting ways that people haven't said before, it can be quite an enjoyable experience. So if I discover something, or my collaborators discover something, we eventually need to tell the story to the rest of the world. Right? That's why we're doing what we're doing. We're trying to advance human knowledge in some basic way. And so just discovering something is not enough. You then have to go and write a publication about it and spread the word. As I get older, I find that I'm doing calculations less and less. I wish that wasn't true, but anyway, I just have not enough time as I would like to actually sit down and get into the trenches and grind out calculations. When I'm teaching, I spend a lot of time preparing lectures, and that's something I take really seriously. I travel a lot, actually, and this is one of the great joys of being a scientist that I had no idea was actually actually existed. But you know, on average, I probably take 5 to 10 trips per year to often to very interesting places. Places like Tahiti. There's conferences in Tahiti that I go to pretty regularly. Later this month, I'll be going to Copenhagen, Denmark. I haven't been there, so it'll be